Hi, we're going to look at this example of an application problem and write a differential equation that models the situation, solve it, and use that to help us answer the question. So let's read through the situation here. We have a student carrying a flu virus that returns to school after break. 1,000 people on campus and all are susceptible to catching the virus. The rate of growth of the number of infected people is proportional to the product of the number of infected people and the number of people on campus not yet infected. All right, so those are essentially our assumptions. There's some data here. After 4 days, 50 people are infected, and then we want to use that to set up a model here. So one of the important things is to clearly state your assumptions. So those are essentially stated for us in the word problem. We then want to make sure that we clearly identify what our variables are. We've got a time, and so I'm going to let t represent our time. I'm going to use days here since this piece of information here is given in days. And we're going to measure that since the first infected student returned to campus. All right, and then the other information here, we've got rate of growth of the number of infected people. So I'm going to let that be my dependent variable, number of infected people after t days. And then we've got some information here about proportionality. So there's a constant of proportionality, and that would be our parameter. All right, so we want to go ahead and write our differential equation. So we're basically going to just translate what is stated in the second sentence into a differential equation. So we've got a rate of growth, that's our derivative there, of the number of infected people. So that's our dn dt is proportional to, so equals k times the product. So we're going to have a multiplication here of the number of infected people, that's our n, and the number of people on campus not yet infected. So the number of people that are still susceptible. So we're going to have to use this fact here that there are 1,000 people on campus. So if I have n as the number of people that are infected, then we would have 1,000 minus n that are not yet infected. This is actually a really basic version of infectious disease models. Usually they have a few more variables. There are some people that are perhaps resistant to the infection for whatever reason to account for, and then all kinds of other things that you can begin to account for as well. But this is a really useful way to sort of understand how infectious disease modeling kind of works, at least at the very basic level. All right, so then we have some other data values here. We have an initial condition. We have at n equals 0, there's one student infected. At t equals 0, one student is infected. And then after 4 days, we have 50 people infected. So we also have another condition here, not really an initial condition, but another condition that at t equals 4, we have n equals 50. All right, so there's our differential equation and initial conditions. That's part of what it asks us to do, write a differential equation that models the situation. And now we'll go ahead and solve it. So this is first order, nonlinear, because when I multiply out that right-hand side, I'm going to have n times n, so an n squared. It is a separable differential equation, though, so I can solve this using the method of separation of variables that we've just recently looked at. All right, so I'm going to scroll up, so I've got space to do that here. I'm going to divide through both sides by n times the quantity 1,000 minus n, and so I'll have this, and then I want to integrate both sides with respect to t. And on the left side, the dn dt times dt simplifies to just dn. They don't really cancel, but they do simplify. All right, so I need to integrate both sides here. The right-hand side is easy. The left-hand side requires partial fractions. So I'm going to go over here to the side and write that out. Okay, so after doing my partial fractions here, I got that both a and b are 1 over 1,000, so I can rewrite my differential equation. I'm going to end up just factoring those out since they happen to be the same constant. All right, and then I'll go ahead and do that integration on the left side. the second fraction requires a little u substitution. You would let u equal the denominator, and you end up with an extra negative sign from that. All right, and I just put the plus c on the right-hand side here. All right, so there is an implicit solution. I do have two parameters in that. I am going to go ahead and solve that so I get an explicit solution, so it's solved for n, and then after that I'll go ahead and find my constants k and c. First thing I'm going to do here is use a property of logarithms so that I have ln of n minus ln of 1,000 minus n. You can combine that into a single logarithm using a property of logarithms. I'll write that over here to the side. All right, so I use that. I'm also going to multiply through by 1,000. So I'll have 1,000 kt plus 1,000 c. All right, and I could choose to absorb that 1,000 into those two constants if I wanted to. I am going to actually absorb it into one of them, but not the other. We're going to look a little bit later in this video at a slope field for the original differential equation, and I want to be able to put in my k into that original differential equation. So I don't want to absorb the 1,000 into my k just because of what I want to do later. I am going to go ahead and absorb my 1,000 into the c, so this next c will be a different c than I had in the prior step, but represents all possible constants, so I'm just going to replace that with a c there. All right, then the next thing I'm going to do is exponentiate both sides so that I can get rid of the logarithm on the left side. And then again on the right side, I'm going to make that same simplification we made a few times with these solutions for these separable differential equations. I'm going to use another property over here. So e to the a plus b is the same as e to the a times e to the b. So I'm going to use that here to separate that into e to the 1,000 kt times e to the c. Absorb that e into the c, so they can rewrite that right-hand side as c e to the 1,000 kt. And again, that c is different than the c we had in a prior step, but that's okay because I haven't really done anything previously where I want to be able to go back and keep track of that c. All right, so to finish solving for n, I'm going to multiply through both sides of my equation by 1,000 minus n, and then I'll combine like terms and get all the n's on one side. All right, at this point I have an explicit solution solved for n. I now want to go ahead and find c. So I'm going to put in my initial condition that when t equals 0, n is 1. All right, so let's go back and put that into our solution. All right, I could leave my solution in this form, and if my math lab is asking you for something like this, it should recognize that that's perfectly fine as long as you get all the fractions set up correctly, so you got the fraction bars in the right place. I would probably choose to do a little bit more simplifying with this one, just because we're going to use it for a few other things. So I'm going to do one thing that might seem obvious to you, and then another thing that maybe might not quite seem as obvious. I'm going to multiply on the numerator and denominator of the fraction by 999. So I'm just multiplying by a form of 1. That will clear the fractions within fractions. When I do that, I have to remember on the denominator to distribute that 999 through to both terms. The other thing I'm going to do is multiply through by e to the negative 1,000 kt. And that's the part that maybe isn't quite as obvious why that is helpful. The reason that is helpful is that when you do that, you only end up with one t in the equation. So there's only one place where your independent variable is in your solution. All right, so when I do that, on the numerator, the 999s will cancel, and the e to the 1,000 kt times the e to the negative 1,000 kt will be e to the 0, which is just 1. So the numerator just becomes 1,000. On the denominator, I'll have to distribute that all through to the 1, so there's where I will have a t, 999 e to the negative 1,000 kt. And then the second term there, everything will cancel, so I'm just left with plus 1. This kind of solution is pretty easy to work with when you're trying to think about what happens long term with this or whatever. So here's a solution. I don't yet have that value of k, so I'm going to go ahead and do that. But one of the things that you can see here, if k is positive anyway, is that it's pretty easy to think about what happens long term with this. That eventually this is going to approach 1,000 as t approaches infinity. In terms of the context of this problem, what that means is that eventually everyone on campus will end up being infected according to this model. All right, so let's go ahead and find k. I was given another initial condition that n of 4 equals 50. So I'm going to go ahead and put that in to find my k. All right, so now I've got this k value here. So I might want a decimal approximation for this. 9.906 times 10 to the negative 4. I'm actually going to use the exact value in my later calculations, but sometimes it's helpful to also have that decimal approximation. All right, so let's go ahead and put in my k value back up into my solution. There's one couple things to be careful about here. Notice that in my k value, I've got a minus sign out front, and in the equation I'm plugging it into, there is a minus sign there. So those will cancel each other out. So when I first did this problem, I made a mistake and left a minus sign in there and then got answers that didn't make any sense. So just be careful about that. So I'm going to put all this in for k, multiply by 1,000, and simplify my answer. All right, so here is the particular solution satisfying our conditions that we were given in the problem, our initial condition, and then also the condition at t equals 4. Might notice there's an e and an ln in the exponent there. There is some simplifying you could do there if you want. I'm probably not going to do that. I am going to, at this point, go look at the slope field actually for the original differential equation and think about what that slope field is telling us, and then think about whether what we've got here makes sense. So let me pull that up. Okay, so here you can see I have d field pulled up. I've typed in the differential equation in the d field equation window. So I have n prime equals k times n times 1,000 minus n. I have my independent variable t. And then down where it says parameter expressions, that's where I've given my decimal approximation for my parameter k. So k equals, and I just typed the decimal expression for it instead of scientific notation. I also set up my window to make sense in the context of the problem. We're given some values at t equals 0 and t equals 4. I set my t window up to go from 0 to 50 just to kind of see what was happening. And then my n axis, I set that up to go from 0 to 1,000. So we're starting with only one person infected, and we know we have a maximum of 1,000 people on campus that would be infected. So we can see that there. And then I clicked graph phase plane, and so I see this slope field here on the right hand side. I can click on here at different places and see some solution curves. So there's one. I'm really interested in the solution curve though that satisfies the specific initial condition we had, which was n of 0 equals 1. So I want to show you how to do that. You can go here to solution and do keyboard input of initial value, and then type in the initial conditions that you have here. So t equals 0, n equals 1, and then if I click solve, we should see that graph there. So a couple things I want to pay attention to about that. I want to make sure that it does appear to pass through 4, 50. So when t equals 4, it does look like that the output of that function is at approximately 50. And then the other thing it asked us to do in the problem was to figure out about how long it takes until 500 people are infected. So we can see from this that it appears that at approximately 7, at about t equals 7, it appears that n is 500. I could verify algebraically that that really is what works by plugging in n equals 500 and solving for t in my equation, and I'll do that really quickly in a little bit here. But from the graph there, you can see that it appears to take about 7 days for us to get to 500 people infected. All right, let's go ahead and I'll just quickly go through that last bit of the calculation there to find out how long it takes till 500 people are infected. Okay, so I did a bunch of algebra there. Maybe skipped a couple steps there, but did a bunch of algebra and got to the end here and got t is 4 times natural log of 1 over 999 all over ln of 19 over 999. And that's about 6.97. That would be in days. So approximately 7 days, which is what it showed on our slope field. So that's a good way to make sure that the results you got made sense with your initial assumptions. Feel pretty confident that I didn't make any mistakes in the calculations this time because they made sense with my actual slope field that I looked at.